So if you have electric fields, so there is a energy in that electric field. Remember in the electrostatics, I told you that there is an energy in the attraction and repulsion of the charges. If a charge particle attract, there is a energy stored in the attractions. If they repel, energy stored in their repulsions. So same energy we can understand in another second way. The second way of understanding is that I can say the energy is going to be stored in the field. Okay, it doesn't mean it's a new type of energy. No, it is not a new type of energy. It is the same energy which is between the attraction or repulsion. So it's another way of expressions. Let's call here as a field energy, right? And because field is everywhere, here, there, everywhere, field is there. So what we can do is we can define the energy in terms of density. So we have electrical energy density. We have electrical energy density. And this is your half epsilon naught E squares. Okay. We have very indirect proof is there for it, no direct proof. Okay. Simply indirect proof is there. So proof is not important here. So just understand here, there is a energy stored. And this is not the energy, it is energy density. Means it's going to be the energy stored per unit volume. Same way, if we have a magnetic field, so in the magnetic field also, it is going to be store the energy. And that's called here as a magnetic energy density. Magnetic energy density. And this magnetic energy density means energy per unit volume here. So that is almost similar thing is here. It's a B square by 2 mu naught. This is our magnetic energy density is there, right? Okay, it's a proof is a quite simple one is there. Not a direct proof, not an absolute proof is there. Simple and approximate proof we have. Approximate in the sense that we have discussed inductor is just like a solenoid, right? I can think of inductor, the simplest inductor is a solenoid. So you can consider here a solenoid, and the solenoid is going to carry some current. So energy of the solenoid, I can say it's a half L I square. That's my energy of a solenoid. Another thing, if you remember, we have discussed inductance of the solenoid is mu naught n squares into the volume. That is the inductance, right? So we can think of inductance as a half mu naught n squares V. That's my inductance into I squares. We also know that there is only magnetic field exists in the solenoid. And what is the magnetic field outside? 0. And inside only we have magnetic field, that is mu naught Ni. So what can I say? I can say it is going to be half mu Ni square by 2 into V. If you multiply with the mu naught and divide with the mu naught, so numerator term I can write in terms of V. So what can I say? I can say that energy is half B square by mu naught into volume. So this is the energy, and that is the magnetic field, and that is the volume in which magnetic field exists. Only in the volume of solenoid you have magnetic field. Outside the solenoid volume, you don't have magnetic fields. So this energy is going to be stored in the volume of V. Energy stored in the volume of V, and the magnetic field is this. Okay, in terms of magnetic fields. So here I can say in the solenoid, per unit volume of the solenoid, how much is the energy here? It's a B square by 2 mu naught. So that is the energy in the solenoid only. Okay, it is not general. But this proof of the solenoid is going to be here more general. Okay? So this proof is not only for solenoid, but it is general proof. Results are going to be general. Proof is not general, but it's going to have, it's a general result is there. So wherever there is a magnetic field, there is an energy stored. And the energy stored is a B squared by 2 mu naught. I hope you understand here. Same way, you can take a capacitors, and for the capacitors, I can prove the electrical energy. The point here is, there is an energy. Okay, so there is an energy stored in the capacitor. There is energy stored in the inductors. And why capacitor and the inductor stored energy? They store the energy because there is electric field and magnetic fields. So wherever there is electric field, wherever there is a magnetic field, there is energy stored. Okay. Now here, one thing you can understand here is, this is my first expression. This is my inductor energy. This is my current energy. And here is a magnetic field energy. So that is my energy in terms of current, and that is my energy in terms of magnetic fields. Magnetic field is created because of current. Okay, and current create magnetic fields. So both energies are same, only expressed in a different forms. So both the formulas are same, just expressed in a different forms. The meaning thereby, wherever there is a field, there is an energy, right? So you have electrical energy, you have magnetic energy. And in my EMI, we have discussed that in the EMI, we have discussed that magnetic field can turn into the electric field. We have discussed na? EMI. Magnetic field, the time varying magnetic field can create electric fields. So magnetic energy could be turned into electrical energy, or electrical energy could be turned into a magnetic energy. So it's not like that these energies are separated. We only think them separated. Nature does not create such a separations. So electrical energy and magnetic energy, they are interchangeables. Okay. So that is an important point to understand here is, due to our EMI phenomena, electrical energy and magnetic energy can be interchanged. So their relation is almost like a kinetic energy and potential energy. So potential energy could be turned into kinetic energy could be turned into a potential energy. The same way, electrical energy and magnetic energies are interchangeables. In that, the biggest example, again, where that happens is a oscillations. That's called LC circuit. LC circuit is the biggest example where your electrical energy and the magnetic energies are interconvertible. You can convert electrical energy into magnetic energy, or magnetic energy into electrical energy. So because my energy go from electrical to magnetic and magnetic to electricals, so it is also going to be have a oscillator natures. So in some books, they are writing LC oscillators, right? Its working is quite easy, but very important role it does play in our natures. Circuit is quite simple. You have one inductor and one capacitors, no battery. Okay, no resistance, no battery. So you have only inductor and you have only capacitors. You have only inductor and you have only capacitors. So in these situations, this inductor is going to be store my magnetic energy, and capacitor is going to store here electrical energy. So suppose that I give some charge. So there is some charge on this capacitors, and there is a current in the circuit. You have a current is there in the circuit. So this based on this rise or falls. So I can say that there's going to be here my potential is going to be dropped across the inductor, and there is a potential is going to be dropped across our capacitors. So if two are connected without any resistance, without any battery, that circuit is going to be called here my LC circuit. That's a very unique and special type of circuit. So till now, whatever the circuit we have discussed, it is quite different from the other circuit. Yes, not.
Sir, from where is the current created, sir, without battery?
Without battery, from where the current is created. I will come to this point. 1 minute. So imagine that there is a circuit. In the circuit, you have some current and you have some charge. So how it begins, we can discuss it in a few minutes. So let's say some circuit is there. In the circuit, you have current and charges are there. So how it is going to begins, you can understand it in just in a moment. So let's say this is going to have a potential is dropped by the capacitors and the potential is dropped by the inductors. So in my circuit, the most important rule is our Kirchhoff law must be satisfied. So KVL has to be satisfied. If we apply the KVL rules, it say that if I'm crossing the capacitors, it is rising the potential Q by C. Then I'm crossing the inductor, it is dropping the potentials. And the net change should be here 0. Net change here is going to be 0. And one thing more you can see here, beta, what is the relation between this charge and the current? If you see the direction of my current, so this direction of the current indicate that charge is decreasing. Okay, so this current is not increasing the charge on the plate. Hello, can you hear me now?
Yes, sir.
It was disconnected. I don't know. So here we are discussing about our LC circuit, or in this LC circuit. Just 1 minute, starting the screen. So okay, screen visual beta. Screen.
Yes, sir.
Okay, see here. Before we analyze here into the RC circuit, so one thing you can see, it's equations. Equation is quite strange. It is quite different from the normal equation circuit we have discussed. To write it the equations, I just written here the Kirchhoff law. So at any instant, that's current is I, charge is Q. So assuming the current I, charge Q, that's my differential equations. It's my Kirchhoff equation, and this Kirchhoff equation is turned into my SHM equations. So meaning thereby SHM equation. Who have this SHM equations? So simple sign of the SHM equation means the variables is going to have a oscillations. Okay. So in this case, my charge satisfies the SHM equation. Right? So charge here satisfies the SHM equation means. So charge in the circuit is not rising, it is not falling. So what happened to the charge? So charge is going up and down, up and down. Just it is going to be execute here sine functions. Because the only solution of my SHM equation is a sine or cos. Sine or cosine. You don't have a log solution. You don't have any other type of function, exponential. No. Only SHM equation, this differential equation solution is a sine equations. So my charge is going to execute here my SHM equations. And the SHM is going to be have a simple forms. Okay. Where my Q naught. Q naught is the maximum charge that you can call here the amplitude. Q naught is basically the maximum charge amplitude. Sorry. So that is my amplitude. And this factor omega is a frequency, right? Omega is my frequency. If you compare with the equation of my SHMs, the coefficient of x gives me here omega squares. And what is the coefficient of x here? Coefficient of x here is a 1 by LC. So give me that this system is going to be oscillate with the frequency 1 by root LC. So this 1 by root LC is the oscillation frequency. Okay. That is the frequency by which your system oscillates. So just like our spring block system has a left and right oscillations, the same way here you're going to be have charge is oscillating. Okay, and what is my this factor of phi? It is just SHM. Remember, it's an initial phase. So phi represent here our initial phase. That represent initial phase, right? So meaning thereby, in this case, my charge is going to be here varies, and is going to be varies periodically. It will go to the maximum. When sine go to the maximum, charge goes to the maximum Q naught. When sine goes to the 0, my charge on the capacitor goes to 0. Okay, right? So it's going to be have a periodic variation. Sometimes charge goes to plus maximum, sometimes charge goes to minus maximum, meaning thereby sometime your left plate is positive, it is increase its charge to the maximum positive, then it will decrease the charge and the right plate is approached toward the positive. So it's going to be have a oscillation. So charges are going to increase. Sometimes charges increase on the left plate, sometimes it will decrease on the left plate, then the charges increase on the right plate, then charges decrease on the right plate. So it's going to be have a kind of oscillating systems, right? So not only charge, if I find out here the current, so current is also oscillating because Sine derivative is a cos. So if you going to write about the current, so my current is dq by dt, and derivative of the sine is my cos. So it'll give me here cos omega t plus phi into omega, right? So it'll give me here this vector here q naught omega cos omega t plus phi. So here current is also oscillating, and the maximum value of the current comes when cos term is maximum. So here I can say what is a peak value or the amplitude. We can say here my amplitude. Peak value of the current is q naught omega. Peak value of the current here is q naught omega, right? And current is also going to be have a cosine variations. Charge has a sine variations, and the current is going to be have a cosine variations. So there is a gap, there is a time lag is between the charge and the current. You know, in the from the SHM, no? If my sine goes to the maximum, then cos goes to the minimum. And when cos goes to the maximum, sine goes to the minimum. So in this case, when my charge goes to its maximum value, your current goes to zero value. And when the charge goes to its zero value, the current goes to its maximum value, right? So it's going to have a kind of oscillating 90-degree phase difference. That's going to be called here as a 90 out of phase. So charge and currents are 90-degree out of phase. Okay. If you relate with the pendulums, okay, if you try to relate it here with the pendulum, so it is similar to the pendulums. Now, in this case, in these situations, the role of the displacement is played by the angles here. This angle role is played by the charge, and its velocity role is played by our current. Displacement is played by our charge, you can say here. So displacement, you can consider here it's a play the role of my charge, and the velocity is going to play the role of my current. When displacement is maximum, velocity is zero. And when the velocity is maximum at the mean positions, displacement is zero. So it's going to be have similar relation. When charge is maximum, current is zero. When current is maximum, charge is zero. Okay. If I think about the energy, so we have two types of energies are there, electrical and magnetic. Electrical energy is stored in the capacitors. So it's Q square by 2C, Q naught square by 2C, sine square omega t plus phi. That is my electrical energy. And what about the magnetic energy? So magnetic energy is a half L I squares, half L I naught squares, cos square omega t plus phi. Right? So my electrical energy vary with the sine squares, and this magnetic energy vary with the cos squares. If you just notice their peak value, they are same. They are same because if I try to find out here this peak amplitude, what is my peak amplitude? It's a Q naught omega. Current amplitude is Q naught omega squares. And what is the value of my omega? The value of omega is root LC. So ultimately, both the amplitudes are coming out to be same. Na? So maximum electrical energy and maximum magnetic energy, both are same. So meaning thereby, if I want to write here my total energy, so total you have electrical plus magnetic, we don't have any third energy. And both are going to be equal. Q naught square by 2C, that's a sine square omega t plus phi. And the amplitude of magnetic energy and amplitude of the electrical energy both are same. Both are same. So when the amplitudes are same, so the factor of sine and cos square, cos square, it will give me 1. Q square by 2c, that will give me here the factor of Q naught square by 2c. Or Q naught square by 2c, it is also equals to half L I naught squares. So point is, your total energy is a fixed one. Total energy is not changing. So what is changing? When my electrical energy is increasing, your magnetic energy is decreasing, because when sine increasing, cos decreasing. When cos increasing, sine decreasing. So meaning thereby, if I try to relate in terms of my energy, your total energy is not at all going to be changed. So when my sine square is 0, your cos square is maximum. And when your cos square is 0, sine square is maximum. So it will go this way, right? Just a minute here. So this red color represents our magnetic energy, and this green color is representing our electrical energy. So when you have a energy, okay, this is my total energy. So total energy is not changing. So sum of the magnetic and electrical energy is a constant. So what is changing? The changing is a shear. Shearing is going to be changed. Just like in our pendulum, kinetic energy goes into potential energy go into kinetic energy. Here, my electrical energy is the rise of electrical energy means fall of magnetic energy. And when there is a rise of magnetic energy, there is a fall of electrical energy. But overall, it is going to be constant. Okay? Overall, it is going to be constant here. Now it's an ideal situations. In this pictures, we assume there is a no resistance, but the resistance is always there. In this picture, we have not taken the resistance. So it's a without friction basically. Okay. Without any loss of energy, without any friction effect, without any resistance effects, your electrical energy and magnetic energies keep on oscillating forever. So it is keep on oscillating. Just like our pendulum, if friction is absent, pendulum is keep on oscillating forever. But if friction comes, then it will slowly die out. The same thing is happens with the resistance. When the resistance comes, the amplitude is going to be die out. But as long as we have pure LC circuits, okay, in my pure LC circuits, so it is an undamped oscillations. On these undamped oscillations, electrical energy go into magnetic energy, and magnetic energy go into a electrical energy. Right? I hope you understand the point over here. Okay, I hope you understand the point here. Now we can, if you understand here mathematically, we can understand it here conceptually also. Mathematically, it's quite easy. It's same as atoms. And conceptually, it is same as our pendulum, but reason is quite different. Oscillation is same as pendulum, but reason here is quite different. Just one moment, not. So let's try to understand that why it is oscillating, why it will oscillate. So suppose that I give a charge the capacitors, I fully charge the capacitors. Okay? I given here fully charged capacitors, and there is a no current, and I'm going to be connected here. So these are situations like a pendulum you have taken to the side and you just leave it. So you take the pendulum on the one extreme. So one extreme is that, and one extreme your x goes to the maximum. Here, my one extreme is charge goes to the maximum, and current goes to 0. This is extreme situations. So you're going to be release it from the starting positions. Okay. Capacitor is there, inductor is there. So if I'm going to now connect here the switch at time equal to 0, the switch is closed, right? So at time equal to 0, switch is going to be closed. So in this case, can you tell me what is the value of phi? What is the value of phi? And then what is the value of my charge at any instant? Charge at any instant of time. And current at any instant of time. Or energy, electrical energy, any instant of time. And of course, you can tell me about the magnetic energy also. Magnetic energy at any instant of time. So this is quite similar to our SHMs. If I relate, it is an extreme position. Okay? Extreme position. This extreme position, we know that phase factor is going to be 90 degree. Okay? If you remember the SHMs, this is representing here phase by 90 degree. Okay, before we go to this mathematical calculation, we can understand here conceptually. I given the charge, I connect the switch, current is 0. And inductor, I told you inductor don't want to change the current. So why inductor will change the current? If conductor don't want to change the current, so why inductor allow the current to be changed in the first attempt? Now the moment you are going to be a switch on, okay, switch is going to be connected. So you can see that immediately it will drop the potential, and this potential is becoming Q naught by C. They are making a parallel combination, right? It's going to be dropped. And the moment it is going to be dropped, so getting here my L di by dt. So potential here is minus L di by dt. So how much potential is there? My potential is going to be dropped. Okay. We know that it's a positive charge. It try to move this way. Okay. So charges here try to move in this directions. So it is going to create a potential drop across the inductors. When it is create here the potential drop across the inductors, it created di by dt, positive di by dt. Positive di by dt means current increase. It is going to be give me the rate of change of current. Di by dt means current is begun to change. Of course, it was zero current. Current was zero. Okay, no doubt current is going to be zero, but its derivative is not zero. No? Now derivative become non-zero. So current is zero, but its derivative is non-zero. So slowly it will gain the current. Okay, so it is begun to gain here the current. So in the inductor is accelerating here. Current is accelerating. So because of my potential dropped by the capacitor across the inductors, to satisfy our Kirchhoff law. To satisfy the Kirchhoff law, it will accelerate. Okay. To satisfy the Kirchhoff law, it will drop here the potentials, and we can say it is going to start accelerating. So situation is quite similar to your pendulum systems. When you leave the pendulum from the rest, there is a accelerations, and these accelerations, velocity is zero, but acceleration become non-zero. Even though velocity is zero, acceleration is non-zero, so it will definitely gain velocity in time. Okay, it is no longer remain zero. So it is impossible that the zero velocity is going to be remain zero forever. Acceleration is coming, so it must change. So it will slowly begin to move. Same thing is going to be happen here. So I'm getting a acceleration. Current acceleration is there, so current will begin to accelerate. Okay, I hope you got the point here. Now this current you can see here one thing more. This current is decreasing the charge. So my current rising, but charge is decreasing. Current is rising, charge here is decreasing. And ultimately, my current goes to the maximum and charge goes to 0. Why current goes to maximum? Same reason here. When charge definitely goes to 0, no doubt in that, because current is taking the charge. No? So this current is taking the charge from the plate. So ultimately, charge goes to 0. When your charge goes to 0, so potential across the inductor also goes to 0, right? Because potential across the inductor and capacitors are same. Both are same. The inductor and capacitors are always parallels. So whatever the potential you have on the capacitors, same is the potential you have across the inductors. So that gives me di by dt 0. And that implies your derivative 0 means function maximum. So current reach here maximum value. So when the charge goes to 0, current reach my maximum value. So it is like a pendulum at the mean positions. When pendulum is at the mean positions, you have a 0x value, but you have maximum speed. Okay? You have Q0, but you have maximum dq by dt. Q0, maximum dq by dt. Same. So to represent a kind of mean positions. Right? Now with that mean positions, next stage here is important here. This current is there and inductor don't suddenly make the current 0. Inductor don't stop because of inertia. So just like pendulum, it does not stop the velocity to 0. It will not stop here. It will go ahead because of inertia. So same here, current go ahead. So current keep on going in the same direction and this side now plate become positive. So initially your charge is positive on the left side. Now where is the charge positive? Charge now begun to be positive on the right side. You're going to have a polarity of the capacitor reverse. So on the inductor, your polarity is going to reverse. Okay. Current direction is not changing. Current is still going the same direction, but polarity is reverse. Polarity reverse. Now with that polarity again reverse, charge accumulate on the plates. These charges accumulate on the plates. And I can say that it's going to now give me here potential di by dt. Here, potential is minus L di by dt. Now potential across the inductors, it is going to be positive Q by C. Means current derivative is negative. Di by dt become negative. So it is going to be slow down the current. So current is begun to slow down. Okay. So charge is accumulating, but current is going to be slow downs. So charge is increasing, but current is now going to be slow downs. I hope you understand the point, yes. So ultimately, what happens? Current is slowing down. So ultimately, current is going to be go to 0. One moment comes when my current is definitely going to 0 because it's slowing down. No? But when current is going to be 0, that means your dq by dt is going to be 0. Current is going to be a 0, means charge goes to max. So it is fully charged. So I hope understand the point over here. So in here now, my charge is, capacitor is fully charged, but in opposite directions. Understand? So it is going to represent my pendulum on the other side, but on the extreme positions. The pendulum is there on the other side in extreme positions. So your charge was initially on the left side positive. Now my charge is on the right side maximum and positive. So pendulum has swing half. Now after that, what happens? Reverse swing. Same thing happened in the reverse orders. So I hope you understand here how that LC oscillation is happening. Just a minute. So in this situation, just like a pendulum, it is oscillating up and down. Again, it is going here left to right. So same way, the charge is increasing left to right, and we can understand it from the potential concept here. In circuit, what is the most important thing here is potential concept. Based on the potential concept, we can analyze its extreme positions. We can analyze its mean positions. The problem is quite easy to solve in a mathematical terms. I'm just trying to explain you here step by steps how it is oscillating. So once again, you listen here. What is the starting condition we have given? In the beginning, you have only charge on the capacitor. There is no current in the inductors. Okay? Charge is only on the capacitors, no inductor current, current zero. So if I leave the circuit here, if I just leave here, will it remain there or it is begun to change? It's begun to change. The first change comes is this charge capacitor has a potentials. The moment you touch the inductor also gain the potentials, right? So my inductor also gain here the potential, same polarity. Whatever the sign we have for the capacitors, same is the sign you have for the inductors, and same value, potential drop. So for inductors, we have potential is minus L di by dt. So this charges on the positive plate, they try to move toward the negative plates. Okay, so they have tendency to move toward the negative plates, and this will drop here the potentials. So if I take it here, potential is negative minus Q by C. In the direction of current, this is positive, this is positive, this one is negative, this one is negative. So in the direction of current, it is dropping. That's why minus potentials. So it gives me di by dt positive, meaning thereby current is going to accelerate. Current is going to here accelerate. So current is accelerating. And if you see the direction of my current, so this current direction is decreasing the charge on the plate. Current direction is taking the charge away from the plate. Okay, so my current here is minus dq by dt. So current derivative is positive, but charge derivative is negative, right? My current derivative here is a positive, charge derivative is negative. So current is rising, charge falling. So current is rising and charge is going to be falling. So anyone have a doubt up to this point? Yes. Current derivative. Yes, Shiva.
So I'm confusing that when to take potential is equals to minus L di by dt and plus L di by dt.
In formula, there is a minus sign. Again, if you want to, yesterday also I told you, if you want to apply the Kirchhoff equations, sign is important. Then minus sign is there. In formula, there is a minus sign. What is the meaning of the minus sign is? The meaning of the minus sign here is its direction is opposite to your current polarity. So in the circuit, suppose your current is going to be flow here. So negative potential means in the direction of current, your potential is dropping. Okay, so this, if you are in the circuit, so in a circuit, your minus, in a circuit, the minus sign give you the polarities with respect to current directions. And if you are not interested in the Kirchhoff equation, just magnitude, so there is no need to take a sign. If just magnitude is important, so sign is not required.
Okay,
Okay.
sir.
Mostly we are interested in the magnitude. So mostly we don't take a sign. But in Kirchhoff equations, when you are in the loop, if you want to compare the potential of two different elements, their sign is important. In Kirchhoff equation, sign is very important. So in Kirchhoff equation, sign has to be taken.
Okay, sir.
Okay.
Yes, sir. I understood.
Yes, Sonal.
Sir, without external push of the charges, how it is moving, sir? How is current generated?
Without external,
Push, sir, like any battery is not there. Just by connecting, how is current created?
no. Here, what is the condition I have given you? Initially, some charge is there on the capacitor. Some charge is given on the capacitor. No? The battery was initially connected to the capacitor. Now battery has been removed and capacitor and only